Hello friends, today we are going to be discussing the jugular venous pressure waveform with you and how to relate it with the cardiac cycle so that we can also understand how to delineate between its abnormalities and relate it with other cardiac diseases. Setting a backdrop, let me tell you what jugular venous pressure is. Why do we measure it in the first hand? So the very important part is that internal jugular vein is the most commonly used vein on the right side. We're looking at the waveforms and the pulsations, and it is directly connected with the superior vena cava to the right atrium. So it is the right atrial pressures that we are trying to measure by looking at the JVP. JVP acts like a surrogate for the right atrium. So whatever is happening in the right atrium, whatever pressure changes are happening in the right atrium is what we want to look at by looking at the JVP. Now, before starting this, uh, I want you to go back to your physics classes where you had studied the Boyle's law. So what we remember from it is at any constant temperature, the pressure is inversely proportional to volume. Now, for those of you who struggle to understand which volume we are talking about here, is the volume which is available for something to be filled with. Now, if I take an example of a balloon filled with water, the water is not the volume we're talking about. The volume of the water is not the volume we're talking about. We're talking about this volume, which is still available to accommodate more water. So this is the volume, and the pressure inside this balloon is called the pressure, which we talk about in the Boyle's law, P and B. Now, if I take another balloon or just fill this same balloon with more water, okay, if I fill this balloon with more water, the volume available now is called the V dash, and the pressure inside this balloon now is called the P dash. So what do you think? Is the pressure dash volume dash is lesser than the initial volume, so the pressure dash will be greater than the initial pressure. This is how we apply the Boyle's law. Now, this example was a balloon filled with water. But now, whatever we are going to talk about is the heart filled with blood. So instead of the balloon, think of a heart. Instead of the water, think of blood. And now let's start understanding the pressures and the waveforms. The very first thing, we are going to draw the waveform. Also remember that whenever the atrial pressure increases, if the pressure inside the atrium is increasing, just think of this pressure exerted on all the walls of the right atrium. So some of the blood will also come back to the JVP, and that will reflect as a crest. And whenever the pressure falls, the volume or some amount of a column of blood will be pulled back into the atrium, and that will reflect on the JVP, etc. So this is a crest and this is a trough, which are indirectly reflecting the pressure changes inside your right atrium, right? So okay, so let's draw the jugular venous pressure waveform. Okay, so in the entire waveform, as you can see, there are three crests, A, C, and V, and three troughs. So actually, the first trough is the part of the same, interrupted by a C. So this is X and X dash. It's interrupted by a middle C, and V is followed by a trough called Y. Now let's understand what each one of these stand for and why they produce a crest and trough in the first place. So A is for atrial contraction or atrial systole. So why do you think an atrial contraction is producing a crest and not a trough in the pressure waveform? Let's understand if this is the normal size of the atrium before contraction. After contraction, what do you think will happen to the chamber size? It will decrease. And since it decreases, what do you think has happened to the V dash? The V dash is the volume available for any blood to come in. It's further decreased. So since the V dash is decreased, what do you think will happen to the P dash? The P dash has increased. And this P dash reflects as a crest in the waveform that is called the A crest. Now, what is atrial contraction followed by? Every systole is followed by a diastole. So X is nothing but the atrial relaxation. Okay, I remember X for relaxation of the atrium. Everything about the JVP is about the atrium. So atrial contraction followed by the relaxation, just the little extra. So as we have understood that when it comes back to the relaxed state, the V dash has increased and so P dash will decrease. So the trough. Alright. Now, along with the atrial relaxation, the same time the ventricle is getting contracted. At the same time, the ventricular contraction is taking place beneath. And when the ventricle contracts, at one point, what happens is these cusps, after getting closed, gets pushed by the increasing pressure in the ventricle. The increasing pressure in the ventricle pushes the cusps into the atrium. And when the cusps get pushed into the atrium, the volume dash decreases a bit. The volume dash decreases a bit and the pressure dash increases a bit, and that produces a little crest in the middle of X and X dash. This crest is called the C crest, and I remember it as cusping. Why? Because these are the AV cusps, the tricuspid cusp coming into the atrium, pushed into the atrium, reducing its volume, increasing its pressure. So this AV cusp is producing cusping of the atrium, increasing its pressure by a bit. That is called as the C. But the C one is not so prominent. So if you're looking at the JVP with your eyes on a real body, in the neck of the patient, if you're looking at the JVP, you'll be able to see the A and the V. Okay, there will be two waveforms which are visible. C is very minor, very subtle, so you can't see it. But still, we study it in the JVP because it has three crests. Okay. Now, what is X dash? X dash is again the same thing. The atria keeps on relaxing because the ventricle is contracting. The ventricle contracts and contracts so much that now the volume of the ventricle is so less, it pulls down the AV cusp away from the atrium. So if now the status of the atrium is such that it has relaxed even further because the AV ring has got pulled down by the contracting ventricle. And since the AV ring gets pulled down, what do you see here in the chamber of the atrium? The volume dash has increased furthermore. And since the volume has increased further, the pressure has decreased and that produces a trough, the falling pressure. So what do we call X dash? X dash is the same. Again, it's relaxation only with the ventricle contracting. Along with what has happened now, the AV ring has been pulled down. The AV ring has been pulled down, producing even more available volume in the atrial chamber. Alright, so that is done in the first part of JVP. Then what is the V crest? So V crest is for the venous filling of the right atrium. Now, since the atria has even more space, as we can see, there is so much of space in the atrium. What will happen? And so much of pressure has fallen down. It will start pulling blood. It will pull blood from the JVP, from the jugular vein, that is from the SVC, the IVC. The blood starts filling. And when the blood starts filling, come back to our example of the balloon filled with water. As the blood starts filling, the volume available falls down, so pressure increases. So this pressure increase produces the V wave. And after that, what is Y for? So I remember it as venous emptying. Venous emptying. Y is for emptying. And when the water in the balloon falls down, because it has emptied its water into the balloon underneath. What is the balloon underneath? The ventricle. So the atria to ventricle blood transfer has produced more available volume in the atrium, so pressure has fallen down and that produced a trough again. So it's very easy to understand, right? This is the A1, the C is for cusping, the V is for filling, and everything about relaxation is X and X dash. Okay, ventricle contracting, but the atria is relaxing. We were talking about the atrium in JVP. And then the venous filling and the venous emptying, producing the second part of the waveform. Now, as we've understood the JVP waveform, let's understand what produces the abnormality. So, the very first thing about A wave we can talk about is absent wave. So, why do you think A is absent? Because the atrium is not able to contract properly. There is a lot of ectopic rhythm going on. When the atrium is fibrillating, it's not contracting, it's just fibrillating, and that happens in atrial fibrillation. So, you won't have an A wave. Then, when can you have a big A wave? A big A or a giant A happens whenever there is obstruction in the part of the atrium contracting itself to empty the blood into the ventricle. So that can happen whenever there is a tricuspid stenosis or a pulmonary stenosis or a pulmonary arterial hypertension. So any of the causes which is not allowing the atrium to contract and push its blood into the ventricle produces a big wave. And there is an extreme big wave, which is called as the Cannon A wave. The extreme big Cannon A wave, which happens whenever the atrium and the ventricles are completely out of sync with each other. Completely out of sync. That means the atrium is contracting at its own rhythm, the ventricle is contracting at its own rhythm, and that is your third degree heart block, which is also called as the complete heart block. Okay, so that is everything about the abnormalities of the A wave. There is abnormal V wave, a very large V wave that indicates a lot of venous filling. So when the venous filling is not only occurring with the SVC and IVC, but it's also occurring a reverse venous filling from the ventricles. When will that happen? Whenever there is a regurgitation. So a very large V wave is seen in tricuspid regurgitation because the venous filling is not only occurring from the superior and inferior venous cava, but also from the ventricles. That is seen in tricuspid regurgitation. Sometimes even ASD can produce the same because the left side of the heart will push blood into the right atrium. So even ASD can produce a large wave. Now, there is very important part about the Y wave, then we have to distinguish between two conditions. One is the cardiac tamponade and the constrictive pericarditis. So in constrictive pericarditis, we have a prominent Y wave, prominent Y. But in cardiac tamponade, the Y wave is muffled or blunted. I'll call it muffled or blunted. I am using the word muffled, though muffled is used for sound, because cardiac tamponade also has a muffled heart sound. So you can remember it that way. That cardiac tamponade also has muffled heart sounds and it has a blunted Y wave. It's because the pericardium around the heart is so much filled with either blood or pus or some other effusion that the venous emptying is not happening with the atrioventricular valve filling alone. There's just no space. There's so much of interventricular dependence. There's no space at all. It's only the atrial contraction that is able to push some blood into the ventricle. Otherwise, no passive emptying of blood can happen. So there is a blunted Y or a muffled Y in cardiac tempo. That's all that we have to remember about these things. And the one last thing that I want you to all understand is how does the ECG correlate with the JVP? So since we know that this is around somewhere before C is when your ventricle starts contracting. Because when it contracts, it pushes the cusp inside the atrium and then it becomes so small that it pulls the AV ring down. So this is the part when your ventricle is contracting. And for the ventricle to contract, you should always have a QRS. QRS corresponds to the ventricular depolarization. So the midpoint between the A and C is where your QRS coincides. The peak of the QRS coincides. This is where I make it QRNS, the peak of QRS just before the CX wave. And before atrial contraction, we have to have the P wave to contract it, to depolarize it. So this is the P wave just before atrial contraction. And after that, since we are going to have this entire part is the ventricular systole, right? Between these two dotted lines. So after that, we have diastole, and just before that, we need to have a T wave so that we can depolarize the ventricles. This is where we have the T wave. And then dy is when the ventricles are relaxing. So all you need to do is just make a dotted line between the A and C, coincided with the peak of R. The entire CX dash up till some part of V is going to be your ventricular systole, and this is how you arrange your ECG. Okay, so let's try to identify these abnormal waveforms. As you see, this is a normal JVP which we have already studied. Whenever you see the very first wave being very big in giant A that was associated with anything causing an obstruction of the atrial contraction for pushing the blood from the atrium to the ventricle. So the atria is contracting very hard. Okay, it's trying very hard to push its blood from the atrium to the ventricle. So that is called as a giant A in tricuspid stenosis, pulmonic stenosis, pulmonary arterial hypertension, tetralogy of Fallot. So all of these conditions can have a giant A. A Canon A wave is seen in patients with atrioventricular dissociation in complete heart block. Right? It's complete heart block. A giant V waves, the V wave, the second part of the waveform is very large. That happens in tricuspid regurgitation. There is a lot of venous filling, not only from the venae cavae, but also from the ventricle. And prominent X and Y descents. So these two descents are very, very prominent, and that is seen in patients with constrictive pericarditis. On the other hand, if this waveform looked like this, so instead of Y descent being prominent, if it was like this, it was going upwards. If it was like this, so a very blunted Y is suggestive of cardiac tamponade. So a blunt Y is cardiac tamponade, a prominent Y is constrictive pericarditis. Okay, so hopefully you've all understood what the waveforms of tubular venous pulsation stand for, how to look for the abnormalities in these waveforms. There are two questions that I want to ask you. Let me know what is Kussmaul's sign and what is Friedreich sign and where do we see it. Please write it down in the comment section if you know. And hopefully we'll be looking for how to measure the JVP in the next discussion of cardiac system examination.